Hello, my name is Henry, and firstly, thank you for choosing to watch my presentation. Today I'll be speaking about vector addition systems with states. Don't worry if you've never heard about these before. I promise that I'll give a nice and gentle introduction to this topic. That I appreciate the fact that this topic doesn't feature in FOCS all that often. This presentation is about a paper I wrote with my five wonderful co-authors. They are Dmitry, Chistikov, Wojciech, Czerwiński, Filip, Mazowiecki, Łukasz, Orlikowski, and Karol Węgrzycki. Okay, let's get started. First, I will introduce a special reachability problem on weighted directed graphs that I'll informally call the never negative and exact weighted reachability problem. So here's a directed graph, and I'll label the edges with integers. An example of this question asks whether there exists a so-called never negative path from A to G of weight 10. By never negative, I mean that the partial sum of the weight along the path always remains non-negative. Okay, so to have a look at this example, the partial sum of the weight of the path obviously starts at 0. And from A, notice that you can only go to B because going to C would incur a weight of -7, putting your partial sum below 0. So, okay, first we go to B with partial sum 2, and then up to C with partial sum 5, then across to E, and notice that from E there is a path from D to G of summed weight -1, and the target weight we're aiming for is 10. So we'd like to get our weight up to 11 using this self loop at E before then traversing down to D and then across to G. And indeed, this is a positive instance of this problem. And I can generalize this problem by adding multiple dimensions. So here's a two-dimensional version of this problem. To give you some idea of the terminology to bring you into my world, I would call this a two-dimensional vector addition system with states. So nodes in a graph I will call states, and edges in a graph I will call transitions. And I'm going to shorten vector addition systems with states to VAS for simplicity, and that too obviously specifies the dimensions. This could be a 3 or 4 or 5-dimensional system, as you'll see later in this presentation. Okay. And to give one more piece of terminology, I will refer to the partial sums along the way as counters. And so now I can ask a question in this two-dimensional system. I ask if there exists a never negative path from A to G to this time a target of weight 4 on the first and 5 on the second counter. And by never negative here, I mean that both components must remain non-negative at all times. So from A, both partial sums start with 0. And again, we can't go to C because we would put the first counter negative. So we go to B and have 2 on the first, 0 on the second counter. Now up to C with 5 on the first and 8 on the second. And now we continue, but this time we cannot use this self loop at E because we would go negative on the second component. So we come down to D with 7 and 5. Notice now from D, even if you go via F or directly to G, you'll end up not reaching the target vector 4, 5. So we have to do something a bit intelligent. We notice actually that there is a cycle from D to A to B and back to D that gives you +1 on the first and +10 on the second component. So then we'll take this cycle twice, and conveniently this allows us to take the transition from D to G directly where we reach the target vector 4, 5. And so yes, this is a positive instance. And yeah, you can ask this kind of problem of higher and higher dimensions, and actually this problem explodes in complexity very quickly. That's not the focus of this presentation because I claim to study simple vector addition systems with states. What do I mean by simple? Well, we're going to study a system called flat VAS. So a VAS is flat if for every state there is at most one simple cycle that contains that state. So here's two examples of VAS. Notice that this is a structural restriction, so I'm not going to bother drawing the vector labels on the transitions. The left system is flat. Notice there is a cycle PQR. And there is a cycle at S, that little self loop, but there are no states with that belong to more than one cycle. Whereas on the right, the system is not flat. Notice that both nodes C and D, or rather states C and D, both belong to two simple cycles. Okay, and in this presentation, we're going to focus on the reachability problem in flat VAS, and this flat restriction indeed makes the reachability problem much more tractable. In fact, for any dimension, and regardless of whether you encode the integer labels in unary or binary, reachability is in NP. This work can be found as early as 1997, but this kind of phrasing in terms of flat VAS has perhaps only more recently been written down. But unfortunately, with just one counter, if your flat VAS is encoded in binary, then the reachability problem is NP hard. It's not too difficult to see how an instance of unbounded subset sum can be encoded into reachability in a flat 1 VAS. However, if the system is encoded in unary, then the reachability problem is simpler. In fact, regardless of whether the system is flat or not, reachability is in NL in both 1 VAS and 2 VAS. And so then the question remains whether reachability is in NL for any higher dimensions or whether it's NP hard. And the first step towards this in 2020, it was shown that reachability in unary flat VAS of dimension 7 is NP hard. This was subsequently improved to dimension 5 and then to dimension 4. And so then the burning question is, what is the complexity of reachability in unary flat 3 VAS, asked amongst these 8 authors across 2 papers. And I don't think that question is hard enough, so we're going to go even flatter than flat VAS. We're going to go to something that is called linear path schemes. So a linear path scheme is a kind of flat VAS where the states and transitions form a simple path between disjoint cycles. So this is the kind of picture you should have in your mind. There's a kind of skeleton path through the middle, and there are simple cycles adjoined to some of the nodes along. And we can go even further to a simple linear path scheme in which all the cycles have length at most 1, these self-loop-like cycles. So that's a simple linear path scheme. And it was already asked whether reachability in any dimension D, at least 3, whether reachability in unary D-dimensional linear path schemes is in P. For our main contribution, we answer with no, that reachability in unary 3-dimensional even simple linear path schemes is NP complete. We know that reachability, regardless of the dimension and regardless of whether it's encoded in binary or unary, is in NP, so it remains to show how it's NP hard. For this, we reduce from 3 SAT, and we have 5 main steps to this. The first, we use the so-called Chinese remainder encoding for SAT that's perhaps not super well known. I will explain it in the following slide. And we will show how to encode the satisfiability of the instance as a conjunction of non-divisibility assertions on a certain natural number. And we'll design a 2-dimensional system, but with 0 tests for asserting non-divisibility. And then we'll concatenate these 2-dimensional simple linear path schemes with 0 tests so that reachability in that system coincides with the conjunction of non-divisibility assertions. Indeed, this coincides then with the instance of SAT. And then at the end, we'll use an additional third counter to remove the 0 tests and therefore simulate them. And so this will be the following slide. I'll show you what the Chinese remainder encoding is for SAT and how this can be used to construct a conjunction of non-divisibility assertions that implies SAT. Okay, first I'll explain the Chinese remainder encoding for SAT with k variables. Let's call them x1 through xk. So first you'll want to pick the first k primes. Let's call them p1 through pk. An assignment will be represented by a natural number. Let's call it n. And the way the assignment is encoded is that for each prime pi, if n is congruent to 0 mod pi, then xi is false, and otherwise if ni is congruent to 1 mod pi, then xi is true. Notice that for, well, at least the second prime 3, there'll be remainders that do not correspond to valid assignments, right? It could be the case that n is equivalent to 0 mod 3. This would not encode a valid assignment. So we need to enforce the assignment's validity by first verifying that n is either equivalent to 0 or 1 mod pi for each i, right? Instead of checking this, we're going to check that we're not equivalent to 2, 3, 4, etc. to up to pi minus 1. And we can represent this as a series, or rather a conjunction, of non-divisibility queries. So we check that pi does not divide n minus 2. That's like saying that we do not have a remainder of 2 mod pi. And then we check that n minus 3 is not divided by pi, and again and again and again until pi does not divide n minus pi minus 1. And second, to enforce satisfiability, let's consider a clause, right? Look at this dummy clause x1 or not x2 or x3. Now, this clause is satisfied if n is equivalent to 1 mod the first prime, that's 2, or 0 mod the second prime, that's 3, or n is equivalent to 1 mod the third prime, that's 5. Notice that this is only falsified when n is exactly congruent to 10 mod, well, the product of these, 2 times 3 times 5. So instead, what we'll do is we'll check that n is, well, not equivalent to 10 mod 3 times 2 times 3 times 5. So we'll check that 2 times 3 times 5 does not divide n minus 10. And now notice that for each of the variables, x1 through xk, we have a conjunction of non-divisibility queries. And for each clause, we have one non-divisibility query. So together we have a massive conjunction over all of the variables and all of the clauses, a series of non-divisibility queries that indeed encodes the SAT instance. So coming back to the rough approach for our main theorem, I've shown you how the Chinese remainder encoding works for SAT, and I've shown you how to encode satisfiability and indeed validity of the guessed assignment as a conjunction of non-divisibility assertions. So next I'll show you how to do non-divisibility in a simple linear path scheme. Okay, so let's suppose, for example, that we want to assert that 7 does not divide the value v. We're going to construct a two-dimensional simple linear path scheme with 0 tests that starts with this value v on the first counter, say. We'll call that counter x, and we'll call the second counter y. And let's suppose the second counter y starts with value 0. We'd like this simple linear path scheme to only be parsable, so be able to get from the first state to the last state, if 7 does in fact not divide v. And we'd like to end up with the original starting values that x is equal to v and y is equal to 0, so that we can then combine these by concatenation and then repeatedly do non-divisibility queries. Okay, so here's the simple linear path scheme. I'm going to talk you through it, don't worry. So the first bit, notice that the second counter y starts with value 0, then immediately has 5 added to it, which allows us to take this first loop, well, up to 5 times. At the same time, counter x has 1 added to it at a minimum, and whatever number of times this loop is taken also added to it. So it's like choosing a value r between 1 and 6 to add to counter x. So then x after the first loop will have a counter value of v plus r. Then in the second section, there's a loop followed by a 0 test on x. And notice, in order to pass this 0 test on x, we need to be able to take this cycle to subtract its value down. And so then we needed the value v plus r to be divisible by 7. And indeed, if there is a value r between 1 and 6, for which v plus r can be divided by 7, then indeed we knew for a fact that v originally could not be divided by 7. And so actually, once we've passed this first 0 test, we knew that the original value v is not divisible by 7. But we're not done, right? Because at this point, if we have indeed passed this 0 test, then we'll have so we'll have 0 value on x and some very large counter value on y. In fact, this counter value on y will be equal to the original value v that has been shifted across, plus an additional 6 counter value. That's because these two cycles do not change the total sum of counter value between x and y, because, well, you're trading 7 and minus 7, and in the first loop you're trading 1 and minus 1. Yet the only counter value injection, so to say, in the system entirely was at the start, when there was 6 counter added, 1 to the first and 5 to the second. So then in the following part, to restore the values x equals v and y equals 0 at the end, let's shift everything back over to counter value x. We do this with this loop by adding 1 to x and subtracting 1 from y, and then by 0 testing y to force that this shift was completed in its entirety, and then we'll just subtract 6 back from x at the end. And so we're done. And so now I've explained step 3. The idea now is to concatenate these two-dimensional simple linear path schemes with 0 tests, so that reachability coincides with a conjunction of non-divisibility assertions. If you remember from step 2, I showed you how satisfiability and indeed validity of a guessed assignment could be represented as a conjunction of non-divisibility assertions. They look of the form v minus 2, v minus 3, etc., cannot be divided by the ith prime. So all you need to do is take these gadgets that do non-divisibility assertions with two-dimensional simple linear path schemes with zero tests and just piece them together one by one. And if you need to subtract, I don't know, 2 or 3 from value from the counter, you just do that with a single transition before the non-divisibility assertion gadget, and then you add that counter on at the end. So you can create a massive stack of these to test non-divisibility over and over again. And notice we also do need to add a little self loop at the very start of the gadget to allow X to have a guessed assignment, some value V that's natural. There's no bound on this value, so we can just have a loop that just adds 1 to X and does not change the second counter. But to show that reachability in 3-dimensional simple linear path schemes is NP hard, well, we need indeed a 3-dimensional simple linear path scheme, not a 2-dimensional one with zero tests. So that's where step 5 comes in. I'm going to show you now how we construct a 3-dimensional system from a 2-dimensional system with zero tests. We'll be adding a counter that will handle the zero tests for us. So for this, we use a technique that was originally developed by Wojciech and Łukasz in 2021 that's known as the controlling counter technique. I've kind of taken a screenshot. The lemma statement's rather complicated from our paper. We've modified the original ideas so that the structural restrictions of flat and simple linear path schemes can be maintained. But roughly speaking, this is a black box lemma that allows us to feed in a d-dimensional vector addition system with states that also has zero tests, and it will spit out a d+1 dimensional vector addition system without zero tests. And the first point just says that, well, if reachability holds in the original, then reachability will hold in the new VAS, and that this VAS can be constructed in polynomial time with respect to the number of zero tests. That's the value m. And the final statement, the moreover part, just insists that we do maintain the structural restriction of flatness or simple linear path schemes. This statement and its proof is quite complicated, so I'd be more than happy to explain it in more detail. If you have any questions, please do ask me. But the main takeaway message, like the purpose of what I'm saying now for this presentation, is that a quote-unquote small number, so like a polynomial number of zero tests, can be simulated by an additional counter. Okay, so that's the 5th step done. We'll then take this massive conjunction of non-divisibility assertions, turn them into 2-dimensional simple linear path schemes with zero tests, concatenate them all together to make one very long 2-dimensional simple linear path scheme with zero tests. And then we'll just simulate the zero tests in between cycles with this 5th controlling counter, this 5th step, the controlling counter technique. And that, I think, concludes this presentation. So I spoke about what one might consider our main theorem, that is reachability in unary 3-dimensional simple linear path schemes is NP hard and therefore NP complete. And this closes a nice line of research on reachability in flat VAS, because if you remember from earlier in the presentation, there was the open question of whether reachability in unary flat VAS is NP hard or not. And indeed, this answers this because, well, linear path schemes are a subclass of flat VAS, and indeed simple linear path schemes are an even further restricted variant of those. We also proved that reachability in unary ultra-flat 4 VAS is NP complete. Ultra-flat VAS are an even further restricted variant of simple linear path schemes, in fact. They do not allow the counters to be updated on the transitions between the simple self loops on the states. So the vectors on the underlying path are all 0. This makes the problem even simpler, and therefore we do not have the same result, but we have that reachability in 4-dimensional systems is NP hard. We have to pay 1 counter for this extra restriction. We have an even simpler model, which we call unitary simple linear path schemes. And here we prove that inverse Ackermann dimensional simple linear path schemes have NP hard reachability. I do not have time, unfortunately, to explain what unitary simple linear path schemes are, let alone unitary inverse Ackermann dimensional simple linear path schemes. And after all, we called this paper the tractability border of reachability. And indeed, we have a p-time algorithm for reachability in unary two-dimensional simple linear path schemes when the initial and target configurations for the reachability problem can be encoded in binary. So that's the case when the system itself is encoded in unary, but the source and target configurations are encoded in binary. This improves on the state of the art, and the algorithm for this is not too complicated and requires sophisticated analysis. But please feel free to ask me questions if you'd like to know more. Thank you very much. That was my presentation.